Okay, can everybody hear me? Yeah. So, good morning. I hope nobody has a hangover. Too much alcohol. So, light polarization is used in retrievals of atmospheric particles. My name is Filip Vanhellemont. I work in this institute. I have too many slides, but let's continue. So there are several activities within Roadmap that deal with the polarized state of scattered light. See the talk by Olga Munoz 2 days ago, and Julia. I think Yannick mentioned it as well. I'm not sure. Is he here? No. Not everyone in the atmospheric community is aware of polarization, its effect on measurements. It can have a big impact on measurements if you are not aware of it. And it's used in atmospheric research, mainly the retrievals of aerosols, clouds, dust, haze, and all the particulate matter, actually. There are interesting things in Roadmap that have not been addressed yet. So about me, I work at this institute since 1996. I have a physics degree. I did a PhD on the retrievals and exploitations of the occultation radiometer data, which was an instrument that was designed at this institute. I was in space from 1992 to 1993, 1 year after the Pinatubo eruption. So the entire measurement data set was completely dominated by the stratospheric aerosol cloud from the Pinatubo eruption, which was, for me, fortunate, actually. This is why I am still in aerosol business, actually. So I did some aerosol dynamics modeling as well in function of the data that I retrieved with this instrument. I worked on a stellar occultation instrument on the European Envisat satellites. Also worked on ACE, which is a stellar occultation instrument, Canadian. I worked on PSCs, which are the stratospheric clouds that are mainly responsible for the ozone hole. Polar mesospheric clouds, also called noctilucent clouds. You have a, oops, sorry. How do I point? Okay. So this is a picture I took 3 years ago at my hometown in Leuven of noctilucent clouds. These are high altitude clouds at about 80 kilometers or so. You can see them at midnight. I think this was a picture at midnight. And I also did some global long-term climatology of stratospheric aerosols with my colleague Christine Bingen. I was one of the people that proposed Altius and got it accepted as an ESA Earthwatch mission. It's a hyperspectral imager. I did some work also on a solar occultation experiment vision on board the Picasso CubeSat. And since COVID, I decided to join the team from Anne-Karin van Daal. And I hope to do lots of interesting stuff on planets. Basically, what is it that I did? UV-vis, near-infrared spectral observations. You have transmittance measurements through the atmosphere. Occultation. Transmittance measurements through the atmosphere at different wavelengths. You convert them into local total extinction at a certain spot in the atmosphere. Here is the spectrum. This is the total extinction. You try to separate the different contributions from the different gases, NO2, ozone, this is the air scattering, this is the aerosol scattering. And sometimes it can be tricky, sometimes it's very obvious. One tricky example is, for example, when the aerosols have a spectrum that is identically the same as the air scattering. Lambda to the -4th balance. So starting from the aerosol extinction that you subtract here, profiles left at different wavelengths, you try to derive microphysical properties of the particles.
A mí me
And
funciona lo que no me
on
deja
the
es
right, I have
entrar
some
en la carpeta.
examples for the Pinatubo eruption.
No,
So
a mí
this
no
is
me funciona.
median size of the distribution, the width of the distribution, and the particle number density of the distribution. Okay, Then you do the scientific interpretation. The cloud comes down. This is number density. The number of particles decrease in time, and the size of the particles increases in time. So the particles coagulate. They become bigger, but you have less of them. But occultation data are very, very limited. And for aerosols, sometimes it can be very frustrating. And the solution is to measure in other directions, because, we know particles scatter in all directions. Occultation instruments only observe in the forward direction. Scattering angle is 0. This is the scattering angle. This is the forward direction. And, we are throwing away lots of information, actually. And there's something else that happens at different scattering angles. So scattering angle not zero. So initially unpolarized sunlight becomes polarized. This polarization depends on the properties of the particle, size, shape, composition, and so on. So we have a simple experiment. Let's think about a pinhole camera, which is just a box with a small hole in it. And at the back of the box is a detector, a photodiode, let's say. And you measure the direct sunlight if you rotate the instrument around the direction of propagation of the light, and you plot the intensity as function of this angle of rotation, you see nothing. If you do the same with scattered light, particles and molecules, you see nothing. Constant. If you look at the reflection of a surface, you see nothing. Why? Because the instrument is not sensitive to polarization. That's it. However, if you do this with a generic optical instrument that contains mirrors, gratings, lenses, things like this, something else happens. Direct sunlight, nothing. For scattered light from particles or molecules, you see this pattern. It goes up and down and up and down and up and down. The pattern repeats itself after 180 degrees, not 360 degrees, 180 degrees. And the reflection of a surface does a similar thing, yes. So something happens when light is scattered or reflected, called polarization, of course. So we have, apart from intensity and wavelengths, we have other properties that are sometimes manifest, sometimes not. Sunlight doesn't have it. Light acquires it after having been scattered or reflected. Optics are sensitive to it. It's called polarization. It's an unfortunate thing because there is another process in physics that is also called polarization. It has nothing to do with this, although they are related. It's polarization of matter. It's a different thing altogether. And of course, the polarization contains information on the molecules, the particles, the scattering, and surfaces. I can also tell you now that it can be annoying or wonderful. Depends on your point of view. From orbit, you have different geometries, of course, that you can use, and some orbits are confronted with polarization, others are not. Solar occultation, no. There is no scattering process. Well, there is scattering process in the forward direction, of course. Stellar occultation, same thing, no. Planetary occultation, suppose you want to measure profiles at the night side of a planet, not on the day, not on the terminator. Yes, because light from planets is polarized. Reflection of the planet. Same for lunar occultation. Suppose you want to do an occultation of Phobos. Yes, around Mars. Yes, you have to take into account polarization. Then you have the scattering of light by the atmosphere, limb measurements. Yes, there's scattering involved. Emission, I didn't speak about this, but sometimes, yes, some emission processes in the atmosphere are polarized. Night glow, aurora, things like this. And then you could look at nadir direction. Of course, there's reflection, yes, polarization, emission, sometimes, yes, fluorescence is sometimes polarized. And I show you just one example of an active instrument. It's LiDAR. It's you can do LiDAR from space. For example, the Calliope mission on the Calypso. Sorry, the Calliope instrument on the Calypso mission. And yes, of course, for LiDAR, it's a scattering process. So yes. Brief history. It starts with the Vikings. I'm not going to show this slide. It's too much, really. It starts with the Vikings. It ends with Chandrasekhar in the 50s. This is an example of a birefringent material. It's Icelandic spar. There is a mine on the east coast of Iceland that still produces these kind of crystals. It's birefringent. It played a very, 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 very huge role in the development of science in the West. But anyway, I'm not going to discuss the timeline. Okay, it's photon, Maxwell theory. Okay, the only thing I'm going to tell about this is this. This is a plane wave, sorry. This is a plane wave. Electromagnetic field has two components. It has a phase factor that depends on time and the propagation direction. It has two components that are complex. So it has a real component, EX0, EY0, and it has a complex factor, which is the phase factor of the X component and the phase factor of the Y component. The two components can be out of phase when these two phase factors are not equal, and it's responsible for the different kinds of polarization. The intensity is just the electric field squared, actually electric field times complex conjugate electric field, and you get the intensity. This is a highly idealized description of light because it is monochromatic, 1 omega, it's coherent. It has a spectral width 0, it has a coherence time infinite. These are the different polarization possibilities: horizontally polarized, vertically polarized, any direction polarized, it doesn't really matter. It's linear polarization in all these cases. Here are the two cases for circular polarization. You have a difference in the two phase factors of the two X and Y, the X and Y component, that is plus 90 degree and minus 90 degree. You get left-hand polarization and right-hand circular polarization. You don't have to remember all this. The main thing is this: in general, it's elliptical. And all these cases are degenerate cases of the elliptical polarization. However, it can turn in one direction or it can turn in the other direction. Now, real natural light is not like this. What happens is that real light is the result of large amounts of atoms, molecules, and particles that scatter or emit in the atmosphere. Different positions, different times, they are moving. So we are dealing with a statistical, a stochastic process with some level of incoherency. Now you can define 3 timescales. Here is the natural period. So at the shortest time scale, you have the natural period of the wave. Okay, for infrared to UV, you have 10 to the minus 12 to 10 to the minus 16 seconds. It's very, very short time scales. You cannot measure this time period directly. Nobody can. Or indirect methods, however, but I'm not talking about this right now. You have a coherence time. This is a time scale in which the polarization ellipse remains more or less constant. Okay? And then you have a measurement time scale that is much longer. So this is the coherence time scale, this here, this is the measurement time scale. It changes all the time, all the time. So this beam has a bandwidth, and we call it in theory of polarization quasi-monochromatic light. It has a bandwidth that is much smaller than the actual central frequency of the light. So you can really speak about, a frequency of the beam, but it has a certain bandwidth. Compare it with, the Doppler, the Doppler shifts or the pressure broadening of spectral lines and things like this. Yeah. So we do have to do some statistics We do a time measurement, time average here. And of course, we have two components of the electric field vector. So we have to, if you want to compute the covariance, you have to have a covariance matrix. However, the electric field is complex, so we have a complex covariance matrix. It's called the coherency matrix. Here it is. And you can compose this matrix in three Pauli matrices that you probably remember from quantum mechanics and the identity matrix. Up, here they are. They have the decomposition I times the identity plus Q times the first Pauli matrix plus U, second Pauli matrix, V, third Pauli matrix. You can put everything together like this, and you can read off the four so-called Stokes parameters. From the properties of these kind of Hermitian matrices, you can derive that I squared is always larger or zero or equal than Q squared plus U squared plus V squared. However, you can make it the equality by introducing a factor P squared. And this thing is called the degree of polarization. It plays a central role in polarization measurements. And it's a number between 0 and 1. 1 perfectly polarized, 0 unpolarized. Stokes, this is Stokes. He wrote a paper about it in 1852. He did it in a completely different way because he had no access to the Maxwell theory. Maxwell started doing his papers about 10 years later. So he used the old Fresnel theory, transversal waves. He did a lot of stuff and he arrived at an operational definition of the Stokes vector. It's 6 measurements actually in total. Here they are, and you combine them, you take sums and differences, and then you get something that corresponds with this stuff over here down, this here. So it's 6 measurements, parallel, perpendicular, parallel, perpendicular, 45, minus 45 degrees, right-hand polarization, left-hand polarization. These 6 measurements you can combine in these 4 Stokes parameters, and it completely determines the polarization state of the light. Most people are only aware of I. Yes, the intensity. But there's other stuff going on that's very important. Yeah. Then there is Henri Poincaré in 1892 published his work on this stuff as well. He had another formulation in terms of the polarization ellipse. You have 2 angles, the orientation angle, the ellipse is oriented in a certain way, and you have the ellipticity angle, which determines the shape of the ellipse. If this angle is 0, you have a line. If this angle is 45 degrees, you have a circle. And these are the Stokes parameters in this new formulation. They look like spherical coordinates. If you plot them on a sphere, you get the Poincaré sphere. And you can describe every polarization state on this sphere. So all linear polarizations, for example, are in this horizontal plane. Perfectly vertical, perfectly right-hand polarization is up here. Perfectly left-hand polarization is up here. And you have 2 descriptions now, 2 coordinate systems, if you wish, IQUV, or I, degree of polarization, and 2 angles. When V, this 4th component, is 0, you have only 3. And it is usually the case for atmospheric research that we only have 3 parameters. IQU, or in the Poincaré formulation, I, degree of polarization, and the psi, this direction angle, the direction of the ellipse. So this is very important. These two formulations, you can use both of them, and both have advantages and disadvantages. Here's another view of the polarization, the Poincaré sphere. It looks like a mathematical device that is useful for theoretical insights and things like this, but actually this is from a manual for a polarization modulator device. And you can meet the Poincaré sphere over there as well. Okay, so this device actually changes the state of polarization of optical fiber light. It goes up and you can program it. So one word about the Stokes vector. We have two notations, S0, S1, S2, S3, or IQUV. Some papers use the first, other papers use the second. These are not elements of a standard vector space. Multiply it with -2, for example, and then this is not possible because -2 times I is not possible. Yeah. Okay, I skip this because this is only for weirdos like me. Yes, natural light is a binary cocktail. Why? Because you can write I, sorry, as a sum of 1 minus p times I plus p times I. The first part is the unpolarized part, the second part is the polarized part. Generalize the Stokes vectors and you get this. Two vectors, the first part is the unpolarized, purely unpolarized light. The second part is the purely polarized light. This is very useful in certain calculations, and it's good to be aware of it. So, spectropolarimetry. Most people are aware of I of lambda, what we measure. Density as function of wavelength or spectroscopic frequency, no, wave number. Now we generalize it to spectropolarimetry. Now you have 4 spectra. Stokes formulation or in the Poincaré formulation, if you wish. For usual atmospheric observations, we can neglect the circular polarization, and we have 3 Stokes Poincaré parameters as function of wavelength. You get a lot more information from this, okay? I have to say something about Müller matrices. You can describe the change in the state of a polarization. So the outgoing Müller matrix, Stokes vector, equals the Müller matrix times the incoming Stokes vector. This is the general form. It's a 4x4 matrix. You have Müller matrices for just about every optical component. If you look at the optical software, it's really written in terms of Stokes vectors and Müller matrices. For example, Z-max. The scattering matrix for particles is also a Müller matrix. Surface reflection is a Müller matrix. How does it work? You just multiply them in the correct order, okay? So you start with the source, incoming solar light that is unpolarized, multiply it by the Müller matrix for scattering. Boom, we have the first scattering. Then you have a second scattering. However, the scatter plane changes, so you have to apply a Müller matrix for rotation. Then you arrive at the mirror. But you have to apply a rotation matrix because the instrument is not in the scattering plane of the second scattering process. So you have to apply another rotation. The Müller matrix for mirrors, the Müller matrix for a grating, and you arrive at a detector. This is how you describe it. It's just multiplication of matrices. It doesn't work with the Poincaré formulation. That is why these unintuitive Stokes parameters are still being used these days, okay? If you want to really understand what's going on, transform it to the Poincaré formulation, and it becomes much more easy. So, how do you measure it? How many independent measurements do you need to measure the Stokes vector? Well, I told you Stokes' definition used 6 measurements. No, you need just 4 because the Stokes vector only has 4 components. If v equals 0, then you need only 3. And using a linear polarizer at 3 angles, you can show, this is the Müller matrix for a linear polarizer. Incoming Stokes vector, this is the outgoing Stokes vector. You can derive, so you take the first row, you multiply it with the incoming Stokes vector, and then you evaluate this equation that you get at 3 angles, and you have 3 measurements at 3 different angles, and you just invert this matrix, and bingo, you have your Stokes vector. Okay, that's how it works. It's very simple. Okay. What alters the polarization state? So we already had molecular and particle scattering, surface reflection, refraction changes as well. Birefringence. The attenuation was the concept that is being used in the physical process that is being used in linear polarizers. There is depolarization by thick clouds or by an optical component called a scrambler. It's really based on randomizing the polarization states, okay? It just mixes everything, and in the end, you arrive at unpolarized light. There's magnetic fields, the Zeeman effect, which is the basis of solar polarimetry. There's the Faraday effect, which is a rotation of the direction of polarization. There's the Hanley effect, which is the depolarization process as well. All of these are used in astronomy or, yeah. And it's not really important for atmospheric research, but nevertheless, it's good to be aware of it. As a rule of thumb, when there is scattering, anisotropic materials or magnetic fields, polarization comes into play. Here's an example. This is observations of the sun by a flare genesis experiment applied on a balloon in 2000 by a team from Johns Hopkins. So you have I, Q, U, V. You see the circular polarization component is quite noisy, so it's very small actually. It's and these are the spectra, and you can see the Zeeman effect. It's actually a line that splits in a magnetic field of the sun, of a sunspot. You have the splitting of the two lines. This is the central line. The spectral splitting, the width of the splitting gives you an indication of the strength of the magnetic field. And the other components, Q, U, V, give you an idea of the direction of the magnetic field. I think that's the way it works. But as you can see, the intensity is the same for both lines. However, Q is different. U is also different. Circular polarization is not so different. So you have extra information in these Stokes components here. However, for our purposes, we are using the full solar disk to illuminate the atmosphere, and we measure the scattering. For the full solar disk, it's not really a problem. We can consider the sun as unpolarized. The full solar disk has a polarization degree of about 10 to the minus 6. Okay? Molecular Rayleigh scattering? No, I'm not going to explain all this. It's just dipoles, induced dipoles by an incoming electric field. You get a secondary scattered wave. This is the scattering pattern. It's symmetric around the direction of incoming light. Like this. At 90 degrees, scattering angle, the light is fully polarized. That's the only thing you need to know, really. This is the Müller matrix for Stokes, for Rayleigh scattering, sorry. The degree of polarization can be obtained from this this Müller matrix for Rayleigh scattering by sending in incoming solar light that is unpolarized. You multiply it with the Müller matrix of Rayleigh scattering, you get this. And you derive the degree of polarization, which is purely a function of the scattering angle Here it is. At 90 degrees, you have 100% polarization. At the forward direction, here it's 0. At the backward direction, backscatter direction, it's 0 as well. For a gas mixture, it's always the same, okay? It's always this. It doesn't change. Not telling you the full story, but I'll skip the details. You can't do spectroscopic polarimetry with Rayleigh scattering. Why? Because the wavelength dependence is always lambda to the -4th. And of course, the degree of polarization is always the same. So you can't make any distinction between the different gases, CO2, N2, whatsoever. However, the fact that this is so robustly constant means that Rayleigh scattering can be concerned as some kind of baseline scattering scenario, and any deviation from this pattern indicates the presence of particles and stuff. Here's an example of sky polarimetry. So it's just an instrument on the ground. You look upwards, you have a fisheye lens, you investigate the entire atmosphere. You have a spectral filter, 450 nanometers. This is clear sky. This is scattering angle 90 degrees. This is the maximum. Once there are clouds involved, the degree of polarization becomes smaller, okay? Notice that even in clear sky, you have values for the degree of polarization that are smaller than 1 in this measurement. It means that there is something else there as well. It's, you know, small particles, haze, things like this. Things that are not clearly visible in the picture, but it's there. What about scattering by particles? Yes, this is our thing, Martian dust. Same principle as Rayleigh scattering is induced dipoles, but now in a particle. All the different molecules or atoms in a particle are induced dipoles. Well, you can do this. You can take a particle, like a sphere, for example, it's discretization, and every single piece is a dipole. And you can calculate the total response, the scattering response. For example, here, this is an example that was published in 2011 by Jurkin and Hoekstra, which is a comparison of a discrete dipole calculation. These are the points, 2 points, and the exact theoretical result, the mean theory for spheres. And the comparison is almost perfect, okay? So this method really works very well. And if it works for spheres, it likely works for other stuff as well. So for example, these black carbon models for soot particles. However, these are very, very computationally intensive calculations. Look at it, for example, you need almost 1 billion dipoles and so on. 700 gigabytes of memory, yeah, okay. Usually people use mean theory, in general, I have to say, so this is the equation for general particles. However, if you make some theoretical assumptions, so for example, a bunch of randomized particles with a mirror symmetry, this shape, F11, F22, F33, F6, F44, actually basically it just means that the upper block diagonal to the right and the lower block diagonal to the left is 0. For spherical particles, it becomes even more simpler. You have F11, F11, F33, F33. These two elements are equal. These two elements are equal except for the sign. Compare these two cases. Yes, you can see for spheres these are equal. For general randomized particles, these are not equal. So the difference between 1 minus F22 divided by F11 is a measure of the deviation of sphericity. It is the depolarization ratio. It is used to derive information on the shape of particles. Scattering by particles, yes. So these are results from the famous paper by Hansen and Travis in 1974. If you don't know, if you really want to know everything about this stuff, this is really a nice overview of the entire field. It's a classic, really. And these are examples for spheres, I think. Phase function, the scattering pattern, a function of scattering angle. So a huge forward scattering peak, smaller backscatter peak. And this is the degree of polarization at the forward direction is 0. This is 0. Backward direction is 0. But you can see in the degree of polarization the presence of things like rainbows. Or here, this peak, this is the glory in the backscatter direction. I'm not going to speak in detail about all the possibilities. This is also from Hansen and Travis. The 4 elements of the scattering matrix. As for spheres, it's just 4. As a function of scattering angle, as a function of size parameter, which is the ratio of the size to the wavelength. Look at it. It's really, really very complicated, okay? This is just for one size distribution. It is very, very complicated. Just to give you an idea, if you have incoming unpolarized light, single scattering on spheres, so you have 2 components of the Stokes vector, I and Q. It depends on wavelength, scattering angle, real refractive index, imaginary refractive index, the number density of the particles, the average size, the distribution width. So you have a 7-dimensional table of 2 values, I, Q. The amount of possibilities is enormous, okay? You can spend an entire career working on this stuff. You really can, as some people probably have done also. Yeah. So, and don't get me started on multiple scattering, irregular particles, mixtures of different compositions, then the dimensionality of this table blows up. Huh? Oh yes, I should mention this. At scattering angle 0, here, this is solar occultation. The only thing you get by solar occultation. The rest you just throw away. I should say something about reflection as well. The Martian surface, usually it's modeled with the BRDF function. And usually people use just a scalar function. So it's just outgoing radiance divided by incoming irradiance. And this is a function that depends on all the different kind of incident and outgoing angles. It's for the scalar equation, it is just, it's just unpolarized light. What about polarization? Well, you do the solution. It's a Müller matrix for all directions. This, for every single combination of angles, you have a different Müller matrix. In the code by Rob Spur, which is this radiative transfer code called VLIDORT, you have where is my, no. Anymore. They have a bunch of choices. Here are the vectorial choices. The earliest one is Mishenko in 1997. And so all these vectorial solutions for the surface reflection are from recent years. So it really is picking up. People are gradually making the transition to the full vectorial state. Okay, that's just about everything I have to say. It is available. If you have the computational time, use it. What about circular polarization? Well, we're going to forget it for usual atmospheric applications. For investigation of life, it's completely different. Here is a nice scarab beetle. This is a picture in just with regular natural light. This is a picture with a left circular polarizer. It completely blacks out, almost. all the information is gone. What does it tell you? It means that the beetle reflects almost entirely in right-hand circular polarization. Okay. This is the Muller matrix of a beetle. It is wonderful, isn't it? The only main point you need to know is this component here to the left. This is the 4, 1 component, yes. So multiply this with incoming unpolarized light, 1, 0, 0, 0. The outgoing V component becomes negative, yes? It's a function of wavelength, of course, but it becomes negative, which means that the beetle reflects almost entirely in left-hand circular polarization. Now, why is it? Because biological organisms exhibit homochirality. In short, DNA always circles in the same direction and not in the other direction, and so on. Or sugars or proteins or if you're interested in beetles on Mars or exoplanets, you have to measure V. Really, you have to. If not, well, don't forget about it. I need to say something about measurement bias as well. Imagine an instrument, a general instrument with a Muller matrix M. It measures the incoming light. So you take the first row of the Muller matrix, you multiply it with the incoming Stokes vector, you get M11IN, M12QN, M13UN. In the Poincaré formulation, you get this. It is expressed in terms of the sensitivity to polarization of the instrument times the degree of polarization of the incoming light times a cosine of the angle between the incoming polarization and the maximum sensitivity of the instrument. Okay? If these two angles are equal, it means that the sensitivity is aligned with the incoming polarization. Okay, so it's 0, and then this thing becomes one. So you might think that the instrument is polarization insensitive, or you don't care about it. Or you might think that the incoming light is unpolarized. So, or PM is 0 or PN is 0. So this second term drops. So you think that your model is I at the detector is M11 times I incoming. To estimate the incoming light just by dividing by M11. However, in reality, you calculate this thing divided by M11, and you get this. From this, you get a relative radiometric bias that is written here. It is proportional to the sensitivity of the instrument. It is proportional to the degree of polarization of the incoming light. I'm giving you an example. We are doing simulations for the Venspec H instrument on board the Envision mission that will be launched within 8 years, something like this. Yeah. It's a nadir instrument, infrared, from this institute, so it observes Venus in nadir. It has a focus on the possible volcanic activity. Anne Karin is the PI. And you can derive approximately, in theory, that the relative bias to your retrievals of the gases, this is total column, by the way, the relative bias on your retrievals is proportional to the sensitivity of the instrument times the degree of polarization of the incoming light. Okay? It's proportional to the sensitivity of the instrument. And this is what is shown here on the right panel. This is polarization sensitivity. It is negative. Don't worry about it. Just look at the positive values. And it's linear. Okay? The slope of this line is proportional to the degree of polarization. So, for example, for a solar zenith angle of 0 degrees, so you're looking downwards, the sun is above, you have a backscatter of angle of, so you have backscatter, yeah. It's unpolarized, you have no response at all, you have no bias, nothing. However, when the sun is at the horizon, you really get very, very huge biases on the retrieval of, this is SO2, yes. And these are the points here. It really blows up for very small degrees of, well, polarization sensitivities. It really blows up completely. So these kind of simulations have been done by Severin and Justin. Where is Justin? Over there. And these kind of simulations are used to formulate a requirement for events package, ESA, LUFS requirements. And we have to specify the maximum allowed degree of sensitivity to polarization of the instrument. Yeah. This is just an example of the degree of linear polarization for different scenarios, the different solar zenith angles. These have been done by Daphne Stam, Technical University of Delft. Now, it's possibly widespread bias due to polarization. I'm showing you a figure from the paper by Suzanne Techtmeier from the University of Saskatchewan in 2013 when it was published. These are zonal mean ozone differences from 1995 to 2010, 16 instruments, solar stellar occultation, limb scatter, emission. Don't worry about it. So there is fluctuation. It's not that small. It's order 5% for ozone. Have a look at this this curve here. This is the instrument called Skiamaki here as well. It's a German instrument. It does limb scatter measurements. And around the same time, when this paper was published, another team from Bremen University did lots of simulations and calculations, and they discovered that Skiamaki has a radiometric error of up to 15% due to radiometric polarization, due to polarization. It's weird because Skiamaki was characterized on ground before flight for polarization. It means that the sensitivity to polarization changes in flight. Okay, so you have to worry about this. Yeah. To avoid the bias for Vence package, we have found a way. We have Vence package has a filter wheel mainly for spectral band selection, but there are a few holes left, and we decided to use a few polarization filters. And then we have devised a method just by taking the full intensity, and you measure the polarization in one direction, and you measure the polarization in the second direction, and you invert the matrix, and okay, you have it. And then there is no bias, of course. Okay, I have to show something about mainly an idea that sprung up in our team recently. The Nomad UVIS channel has a diffraction grating that's sensitive to polarization. To the left, you have a schematic picture of the UVIS channel. This is the grating. You also have two mirrors, two reflection events. Only for the grating, this is the response as a function of wavelength. This is for, again, I can't read. It doesn't matter. One direction parallel to the grating lines, one direction perpendicular to the grating lines. It's not zero, it's actually quite significant. So the Nomad UV vision are possibly biased. Okay, but this is a pessimistic point of view. If you have a way to characterize this behavior, then you have polarimetric capabilities for Nomad. Huh? How can we characterize it? Well, perhaps we could find a way to observe a polarized light source to calibrate this. Yes. Another possibility is just to model the behavior. So we have this figure, and we can do some calculations for the two mirrors here, which shouldn't be too difficult, and then you can characterize this. One possibility to do a calibrating measurement is to do a limb measurement of a dust-free or an ice cloud-free atmosphere. So you just have Rayleigh scattering. You know what Rayleigh scattering does in terms of polarization. And then, okay, you're done. So I'm not sure if Mars ever has an atmosphere without dust. Probably not, but how many time do I have left? 8 minutes? So there is another idea that maybe should be investigated. Scalar versus vectorial radiative transfer models. For example, for the nadir observations, we use the scalar radiative transfer model. Basically, it is this. It is just the multiplication of the different processes, the Muller matrices. In a vectorial radiative transfer model, you just multiply all the matrices. In a scalar radiative transfer model without polarization, you just multiply the first element. Okay, this is the model for a scalar radiative transfer. Well, the product of all Muller matrices, and you take the first component, does not equal to the product of the first component of all Muller matrices. It's a difference. So they should give two different results. Even if you are only interested in the intensity, it plays a role, polarization, in the radiative transfer. And I don't know really what the magnitude is, but we at least should investigate it. Yeah. I have some concluding remarks, and this is my opinion. I think every planetary atmospheric observation should have basic polarimetric capabilities. I really do. To avoid bias, for inflight calibration, and of course the aerosol cloud retrievals. The only exception is solar and stellar occultation. I've recently started, recently, a couple of years ago, I started doing this. It isn't that difficult. It seems difficult. It isn't. It's just a vectorization or a matrixification. I don't know if this word exists, of everything that we are familiar with, the spectroscopic measurements, the scattering phase function, the instrument response, the surface reflectance. These are all scalar functions. You just use matrices and vectors instead of the scalars. But the payback is huge. And with this, I thank you.
That was very interesting talk.
Okay.
Any questions?
Thanks, Philip, because with your lecture, I start to understand polarization, which is amazing. Could you elaborate a bit more about the applications, like retrievals of aerosol, cloud? So what is the importance, and how can we use polarization to do these things in what nadir viewing?
Nadir, yes.
Okay.
Well, nadir is just reflection of the surface, right? There is already incoming unpolarized light already becomes polarized. Then you have, if you go upwards from the surface, it's just a forward direction. So the polarization effect shouldn't be too big. However, if you have thick clouds and things like this, for example, Venus, yes, there is multiple scattering, and then it becomes important. Does this answer your question? Just yeah, absolutely. Yes. Yes, actually, it is being done routinely for Earth observations. Huh? So people now are using polarimetric observations to make the distinction between vegetation and ocean and rocks and things like this. So just by looking, the V component of the Stokes vector, you know, associated with life, is used to make a distinction between vegetation or, you know, different kinds of vegetation, forest, grass, things like this.
In fact, I thought it was a stupid question, so I didn't want to ask, but could you use this V component to find possible bio
Yes,
indicators on other planets?
I know what you're going to ask. Yes, of course. Yeah.
Okay, that's very interesting. Just with the polarimeter, you can discover life.
If you're interested in astrobiology and things like this, use V. Absolutely. By the way, the other, take for example an exoplanet. You have a star, and you have a planet close by. The starlight is unpolarized. The light scattered by the planet is polarized. You can make a distinction between the two. No.
Hey, Philip, question. One, are you saying that there's no non-biological natural source of V?
No.
Even calcite, you know.
No, it's possible. For example, a multiple scattering process can produce circular polarization. A second order multiple scattering can produce a V component.
Caution, just by detecting V, you don't detect life.
No.
Okay.
No.
And then second, for exoplanets, wouldn't the interstellar medium act as a depolarizer to reduce our sensitivity to polarization?
My intuition tells me no, because it's in the forward direction, you know.
Thank you.
In the previous to last slide, you mentioned, so for a given instrument, you can actually compute effect of polarization, errors, gratings, whatever.
Yeah.
Is this really realistically knowing the instruments, or is it better to measure it before you set it off on flight? And
no, you should measure it before setting it off on flight. But if you haven't done it, then this is the only possibility. So you take the blueprint of the instrument and the angles and so on, and you have theoretical results for mirrors. For gratings, yes, also, but it depends on the type of grating and so on. But you can do an estimate.